Dear students, this is the last topic of our electrochemistry, electrolytic conductance and conductometric titrations. So, see, we have two types of conductor of electricity. One are metallic conductor and other are electrolytic solution. So, this is a conductivity cell. First we see the metallic conductor. Metallic conductor. So metallic conductor conducts electricity through free electrons. So I'm not going to talk about this conduction by metallic conductor, because in physics all of you are very much clear, and here many topics, many concepts of this you have already gone through in physics. See here, electrolytic solution as a conductor, electrolytic solution conductor. So they electrolytic solutions conducts the electricity through ions. They conducts the electricity through ions. And more precisely you can say hydrated ions. Right? And all of you are knowing that when ions gets hydrated, their effective size will increase. So the ion which is less hydrated have more conductance, more electrical conductance compared to the larger ion, right? So one basic difference between these two, metallic and electrolytic conductor, is that with rise in temperature, the conductivity or conductance of this metallic conductor decreases, but electrolytic solution, the conductance of electrolytic solution increases, right? So this is a fundamental difference between metallic conductor and electrolytic solution as a conductor. So the conduction of electrolytic solution, this is very important point. The conduction of electrolytic solution increases with rise in temperature. So the question arises, why? So the question arises here, why? Why the conductance increases with rise in temperature? So the answer is, with rise in temperature, the following interactions are decrease, thus conductivity or conduction increases. So what interaction? Solvent interaction, solvent solute interaction, basically here ions, and ion interaction, right? So all these interactions are decreases with rising temperature. Therefore, this conduction or conductivity, whatsoever parameter you are taking, that is increases with rising temperature. So this is the fundamental difference between metallic conductor and electrolytic solution. See, the cell which is used in this measurement electrolytic conductance by this solution, that is called conductivity cell. So this cell is called conductivity cell. Conductivity cell, right? And see, AC current we are using here. Which current? AC current. If you use DC current here, then what will happen? When you use DC current, instead of movement of ion, you will get discharge of ion, means electrolysis will start. So AC current is used here, right? See, this is the cross section area of these two plates, and this is the distance between these two. So if you see here, so this is the cross section area, and this is the length between this. So we can assume that the solution which is present in between these two, we can consider this is a wire equivalent to wire, and a potential difference V is set between these two electrodes. So I am considering this portion only. I am not considering the whole solution. So if we consider this, solution between these two electrodes as a wire equivalent to wire, so Ohm's law is applicable here also. So you can write V is equal to I into R, right? So first equation, all of you are knowing this equation. V is the potential difference between the electrodes. V is the potential difference. I is the current, and R is the resistance. Right? Resistance of what? Resistance of solution, right? Which solution? Solution having ions. So they are also, offer some resistance, because when ions are moving inside the aqueous medium, so every ion is moved with its hydrated sphere, and when layers are moving like this, then there is a friction between the ions, and that offers the resistance here. So R is the resistance of solution. How to measure this resistance of this solution? Wheatstone bridge you can use, right? So this is measured by, and all of you are knowing what is the principle of Wheatstone bridge. So I am not going to discuss here, right? Measured by Wheatstone bridge. Wheatstone bridge, right? And you know this, as in the Ohm's law, all of you are knowing this R is directly proportional to L, length of this wire, and inversely proportional to cross section area. So this is equal to, you can write here, rho into L by A. R is equal to rho into L by A. This is equation 2. So one more term is here, rho. Rho is called specific resistance, right? Specific resistance, and it depends on the nature of matter, and I mean nature of ions, right? Nature of ions. So these two formulas, all of you are clear. And one more thing I would like to explain here, that see, this conduction here is taking place through hydrated ions. So if you use normal water here, see, if you use normal water, so in normal water already H plus and OH minus are there. So how to you eliminate this? How to eliminate this conduction by this water? So there are two ways. There are two ways to eliminate the conduction by the ions of water molecule, because after making solution, when you are experimentally determining the overall conduction or conductivity, so it is not possible for us that I mean a conduction shown by the solution, we can eliminate this H plus until or unless we had not make any provision for that. So this is the difficulty here, that water also contributes some H plus and OH minus. So there are two ways to eliminate this. Either you take so pure water that it is free from H plus and OH minus. But remember, you cannot make water free. So the second method is, what you have to do one blank reading with this. You take only water here, okay, and note the reading. And after that, you make the solution of given salt in that water, and again you measure the conductance, and you have to subtract the conductance offered by water from the solution. Then you can get the conduction shown by I mean given salt solution, right? So this is the exact experimental way to determine the conductivity or conductance offered by any I mean solution, salt solution, right? So here we are using conductivity water, right? Conductivity water is nothing but it is the purest form of water, right, for this conduction. So remember by this point, how to eliminate the contribution of water. There are two readings you have to take. One is blank reading, you can say, and other is what and in scientific terminology, in experimental terminology, it is called control. So one is control and other is your sample, right? So control contains pure water in which you have made your solution, right? So in this way you can determine. Now see, uh, this is specific resistance. So specific conductance. Here we have, to explain the conductivity, we have specific conductance. So specific conductance. This is written by K, small k, and pronounced as kappa. Kappa. This is equal to 1 by rho. And 1 by rho is equal to reciprocal of the specific resistance is called specific conductance. So 1 by rho is equal to, we can write 1 by R into L by A. 1 by R into L by A. So this is equation 3. So this is very important equation for us. So this is equal to 1 by R is called conductance. 1 by R is called conductance. Conductance. usually we are writing this with G into what is L? L is the distance between two electrodes, and A is the cross section area of this electrode. So this is constant for a given cell. So this is called cell constant. Cell constant. For a given cell, it is constant. So kappa is specific conductance. Kappa is equal to this equation 4. And what is the unit of this? So unit of this is, unit of kappa is C, 1 by R. So 1 by R is the conductance. So what is the unit of this? So we have different units, but you can write here ohm inverse. Ohm inverse. And if you take here centimeter, so centimeter by centimeter is square. So this ohms inverse centimeter inverse, right? Ohm inverse centimeter. So L is the centimeter, this is centimeter is square, so centimeter to the power minus 1. And in 1 unit, this ohm inverse is called mho centimeter inverse, right? Or you can say SI unit. What is SI unit for this? So SI unit for this is, you can say Siemens, right? So Siemens per meter. So SI unit, SI unit for kappa is Siemens. So this is SIEMENS, S and meter inverse, right? Siemens meter inverse. But usually we express in centimeter, right? So, but you should know what is the SI unit for this, right? So this is a specific conductance. So how to define this specific conductance? Definition, and this is very important as well. So if you take here L is equal to 1, L is equal to 1 centimeter, and A is equal to 1 centimeter square. So if you take this, so it becomes equal to the 1 centimeter cube. Means this is 1 centimeter, this is 1 centimeter, this is 1 centimeter. So this is 1 centimeter cube. So basically, listen carefully. This is very important. Specific conductance is the conductance shown by the ions present in 1 centimeter cube of the solution. 1 centimeter cube of the solution. See, 1 centimeter length and 1 centimeter square cross section area. So it becomes equal to the 1 centimeter cube, 1 centimeter cube of solution. So you can say that we have a cube with dimension 1 centimeter, and whatsoever the ions present in that, whatsoever conductivity shown by those ions, that is called specific conductance. So specific conductance defined as the total conductance shown by the ions, present in 1 centimeter cube of the solution. Right? 1 centimeter cube of the solution. Okay. If other things are what? Constant. So this conductance, the magnitude of this conductance depends on various factors, like, and mainly three factors. Mainly three factors. So on what factor? Number of ions. Suppose that if you have two different electrolytes, one is producing less ion, other is producing more ion. So obviously, which electrolyte producing more ion have more conductance, right? So this conductance depends, magnitude of conductance magnitude of conductance, specific conductance, basically conductance depends on the following factors. Following factors. Number one, number of ions. Number of ions. Number two, charge on respective ions. Respective ions. And third one is the ionic mobility. Ionic mobility, right? See, these two terms all of you are familiar, but ionic mobility you do not know. So ionic mobility, what is ionic mobility? So ionic mobility is, so this is as the name itself suggested. So this is related to something related to the motion. So see, ionic mobility is the ionic speed, means speed of ions, basically ionic speed in centimeter per second, right, unit, divided by the potential difference, right, potential difference per unit length. So in physics, all of you are knowing what it is called. So potential difference divided by the distance between the electrodes. So this unit of this is volt, and this is distance between electrodes. So this is in centimeter, right? So what we get the unit for this? The unit of this ionic mobility, see, centimeter, centimeter, centimeter square per volt per second. So this is the unit of what ionic mobility. And for cations, usually it is a represented symbol. Ionic mobility is represented by U. So this is represented by U plus for cation, and U minus for anion. So cation and anion both will contribute in the conduction of electricity, right? So this conductance depends on the number of ions. More the number of ions means if your electrolyte is strong, obviously it will provide more the number of ions, so it has more conductance. But see, there is one problem. Problem is that if you change this volume, this, how to make this 1 centimeter cube. So it is now, it is advisable, it is difficult for us that the total contribution of conductance present in the total solution, it is not, I mean, we cannot get this, okay, we can get by measuring the volume, okay, that this volume is this, so how many cubes we can make in that volume, so accordingly we can manipulate, right? But it is very difficult to measure this, I mean, directly. We can manipulate, but it is very difficult to direct measure directly. So for direct measurement, we are using another term. Okay, one more thing. How this concentration? See, if you see this equation, there is no I mean term in this equation which involves the, I mean, concentration of electrolyte, concentration of solution, and which is very important, because if you dilute some solution, so number of ions may increase, may constant. Why I am telling may increase or may constant? You know, if electrolyte is not fully dissociated, then if you dilute, with the dilution, degree of dissociation increases, so the number of ions will increase. So this term has no, I mean, feeling of chemistry, you can say, eh? Because there is no concentration term. All these terms are the physical parameters, like wire. So no concentration. So I mean, this term is not give the feeling of what, chemistry. So some concentration term is important to add here. So I mean, direct measurement of this specific conductance is difficult for us because we cannot directly measure it. We can manipulate it, no problem. We can manipulate it, but we cannot directly measure it. So for this purpose, we have two different terms: molar conductance and equivalent conductance. Right? So now see what is molar conductance. This is very important. Molar conductance. So see again the problem. I mean, you should understood this molar conductance, because this is intensive in nature. This is intensive because you cannot add or subtract this. Molar word is attached here. So molar conductance, this is represented by lambda m. So mathematically we can define this. Lambda molar is equal to kappa into volume in ml, having 1 mole of electrolyte. So this is the basic equation. So how we can transform it? See, kappa into, in place of V we can write here 1000 by molarity. So molar conductance is equal to, you can write this, right? How? See, molarity is equal to, you can write molarity is equal to 1 mole divided by V in ml multiplied by 1000 ml per liter. So all of you are knowing this formula. So in place of V, what you can write? In place of V, you can write 1000 by M. So this is the important formula for you people. You frequently you have to use this formula for the calculation of molar conductance. So the molar conductance, now you can define the total conductance shown by the ions present in what? 1 molar solution, means solution having 1 mole electrolyte, right? 1 mole of electrolyte in the given volume, in the given volume. Whatever volume you can take, no problem. But 1 mole should be there. 1 mole of electrolyte should be there. So molar conductance, we can say the total conductance shown by the ions present in what 1 molar ion present in the solution having 1 mole of electrolyte. This is the molar conductance. So we can define the molar conductance is the total conductance shown by the ions present in a solution having 1 mole of electrolyte. Now again the problem will arise that electrolyte is weak or electrolyte is strong, and what other effect of dilution. So many factors are there, so we will discuss one by one. So what is the unit of this? Unit of molar conductance. Now what is the unit of kappa? We have written here the unit of kappa. This ohm inverse, centimeter inverse, right? Ohm inverse centimeter inverse, and this molarity. What is the unit of molarity? Moles per liter. So moles per liter here, this molarity. So what should be the unit here? Here you will get mole inverse and centimeter cube, right? Because see, what is the definition? Volume in ml. So ml, 1 ml is equal to 1 centimeter cube. So now this unit becomes equal to ohm inverse centimeter square per mole. Right? See here, this is molarity, 1 mole per liter, and you know this 1000 centimeter cube, 1000 ml, right? Because you know here volume in ml. So 1000 here, this is the unit centimeter cube in place of ml. So your unit becomes equal to this, or you can write Siemens centimeter square per mole, right? So this is the unit of molar conductance. Now see the similar term we can write equivalent conductance. Equivalent conductance. So lambda equivalent. And same formula we have for lambda equivalent as well. So lambda equivalent, what is the unit of this? Siemens centimeter square per equivalent is equal to kappa into 1000 divided by normality. Just change molarity with normality and get the equivalent conductance, right? No need to just here one in place of 1 mole, here 1 equivalent, and now you can make a relation between these two. So molar conductance and equivalent conductance are related with this normality by molarity, and you know normality is equal to molarity into n factor by molarity. So this is cancelled. So you can write lambda molar is equal to lambda equivalent into n factor, right? So this is the relation between lambda m and lambda eq. The relation between lambda m and lambda eq, right? Now see, one very important question is asked here: effect of dilution. Effect of dilution. Dilution, right? Number one, on specific conductance kappa. Specific conductance kappa. You know kappa decreases with dilution. Means with increase in dilution, the specific conductance decreases. The question arises here: why? You know, this specific conductance is defined as the conductance by the ions present in the unit centimeter cube of the solution. Means 1 centimeter cube of the solution, right? 1 centimeter cube of the solution. So on dilution, number of ions increases, but the number of ions are not increasing in the same ratio as the volume increases. Suppose that if you have taken 1 mole of NaCl or KCl, and on a certain volume you have, and if you increase the volume double, it is not possible that the degree of dissociation becomes double. I mean number of ions double. No, not like that. So the proportion in which volume increases, the number of ions are not increasing in the same proportion. So the specific conductance decreases. Now see, molar conductance. Second point: molar and equivalent conductance. Molar and equivalent conductance, lambda equivalent, they are increases with dilution. Again, the question why? So this time, total number of ions increases, and we, have not, required this volume, because you know it is independent of volume. See here, there is no, term here of the volume. See here, we have replaced this. Only requirement is that it has 1 mole of electrolyte. Volume should be anything. So once you are diluting this, total number of ions increases. So this will increase, but not infinite time. It increases with dilution up to the full dissociation of full dissociation of an electrolyte. Once electrolyte is fully dissociated, then it becomes constant, right? Once the given electrolyte given electrolyte is fully dissociated, this lambda m and lambda eq are constant with highest magnitude, with maximum magnitude, right? With maximum magnitude. And fully dissociated, this is called infinite dilution. This state is called infinite dilution state. So the infinite dilution state of any solution, these two are maximum. And this kappa is minimum in that situation. Kappa is minimum because in that case, in per unit volume, your number of ions are minimum. So in per unit volume, number of ions decreases, overall number of ions increases, right? So this is the molar conductance, equivalent conductance, and specific conductance with unit, right? Now let's do some problem. Now see the question, one example. The resistance of n by 50 KCl solution is taken in a conductivity cell was found to be this. The specific conductance of KCl is this, mole per centimeter inverse. The same conductivity cell was filled with CaCl2 solution at this concentration. Now the measured resistance was this. Calculate the cell constant of the conductivity cell. See, this first part of this calculation, conductivity cell constant basically this L by A. See, cell constant is equal to L by A. It is not determined geometrically, means with the help of vernier calipers you are not going to determine what is the length and what is the cross section area. This determined experimentally, and for this we are taking reference salt is KCl, right? So cell constant, it is determined experimentally by using KCl solution as a reference. So this first part of this question is given to calculate this L by A only. After that, by calculating this, you can use this value for the experimental determination of the given salt. So the given salt is CaCl2. So you have to calculate specific conductance, kappa, equivalent conductance, and molar conductance of the CaCl2 solution. But cell constant of the conductivity cell, see, although it is clear in this question that calculate the cell constant of the conductivity cell first, and then then the conductance and everything for of the calcium chloride. So this is very important. If you are not clear with this, you cannot solve this problem. So first you have to calculate L by A of the conductivity cell by using KCl solution as a reference. Okay, let's do. So for this L by A, what is required? What you have, see, resistance is given. So you can calculate Z. And so what is, this the specific conductance kappa for KCl is given. Kappa for KCl is given. This is 2.768 into 10 power minus 3 mole centimeter inverse. And R for KCl solution is given 457. Oh, right? So you can write here kappa is equal to 1 by R L by A. So you can write here kappa by G. Kappa by G is equal to L by A. That is cell constant. Cell constant. Right? So you have kappa, you have G. G is equal to 1 by R. So first we have to calculate G is equal to 1 by R. So this is equal to 1 by 457. So this is equal to 1 by 457. It is 0.0000218, right? So put here this value 2.768 into 10 power minus 3 divided by 0.002188 is equal to cell constant. So cell constant is equal to solve this and you will get what is the answer? 1.265 centimeter inverse. Centimeter inverse, right? So this is the answer of the first part. Now come to the calculation for this calcium chloride. So specific conductance, first the conductance of calcium chloride, C. So G for calcium chloride is equal to, this is the second part, G for CaCl2 is equal to 1 by R for CaCl2. So what is the R for CaCl2? What is R for CaCl2? The R for CaCl2 is 1050, right? 1050. So this is equal to 1 by 1050 and this is equal to 9.524 into 10 to the power minus 4. Yes. Okay. Now see third part, kappa for CaCl2 is equal to G for CaCl2 into cell constant. And you know cell constant is constant now. So this is equal to 9.524 into 10 to the power minus 4 multiplied by cell constant is 1.265, right? So this is equal to, what is the answer for this? 1.2 into 10 power 1.2 into 10 to the power minus 3 mole per centimeter. So this is the answer of the third part, and this is the answer for the second part. Okay, now we have calculated G for calcium chloride, kappa for calcium chloride, now equivalent conductance and molar conductance. Okay, so fourth, lambda equivalent is equal to kappa for calcium chloride into 1000 by normality with respect to the calcium chloride, right? So this is the equation. Now kappa we have calculated already, 1000 is 1000, normality. So normality is equal to strength in grams per liter divided by equivalent mass. So strength in grams per liter they have given 0.555 divided by what is the equivalent mass of calcium chloride. So equivalent mass of calcium chloride is equal to molar mass by 2. So this is equal to 111 by 2. So this is 55.5. So this is divided by 55.5. So this is equal to 10 to the power minus 2 grams equivalents per liter. Equivalents, normality. Normality is the number of equivalents per liter. Equivalents per liter, right? So now you have to put the value here. Kappa you have calculated 1.2 into 10 to the power minus 3 into 1000 divided by this normality is 10 power minus 2. So this is equal to 120, right? Mole centimeter square per equivalent, right? So this is the answer of fourth part. Now molar conductance. So fifth part. So you can use this relation molar into molar conductance is equal to equivalent conductance into n factor. So directly you can calculate molar conductance is equal to equivalent conductance into n factor for CaCl2. So n factor for CaCl2, so CaCl2 is a salt. So total charge on cation or total charge on anion Ca2 plus 2Cl minus. So total positive charge or total negative charge, so n factor is equal to 2 here. So this is equal to 120 into 2 is equal to 240 mole centimeter square per mole. So this is the answer. Right? So in this way you can calculate all, you have calculated all the parameters, right?